So basically, this is a work that I've been doing throughout my PhD, and since arriving in Australia working with Rotary, I've been continuing to work on this topic. And so here are going to be a few comments towards the end about the ongoing work, but I was mainly asked to present the paper that's been recently published. Now, for today's talk, I have four specific blocks that I want to take you through. First of all, I want to go through motivation, why we need to do that. Then why we need to reconstruct Mantle in time. Then I'm going to talk about my method of choice, which is the Adjoint method. I'm going to explain how it works. Then I'm going to take you through the recent publication of Reconstruction Models of Dynamic Topography. I'm going to show some examples and take you to some three regions of Australia, Africa, and North America, talk about some of the observations and some of the reconstructions. And in the end, I'm going to talk about what we've learned basically from these models. Now, mantle convection is one of the primary forces that shapes the Earth's surface. The Earth's surface moves both laterally and vertically in response to that. The vertical component is what we geodynamicists call dynamic topography. Now, there is an ongoing debate about the amplitude and wavelength of dynamic topography in our community. But one of the ways to resolve such debates is basically to put additional constraint on dynamic topography. For example, adding time constraint to dynamic topography. What is the evolution of dynamic topography such that it ends up at present day? Now, to have such reconstructions, one of the first steps to have some kinematic frameworks where we describe how the motion of the Earth's surface has been. This is basically plate reconstruction models that we have nowadays. Now, these models have progressed so much for the past decades. And now these are getting better and better. They're going deeper in time. Now, in addition to this kinematic framework, we also need a dynamic framework that describes the forces from the Earth's mantle, which is basically mantle convection. Now, traditionally, mantle convection has been shown with these cartoonish figures. Beneath the ridges, we have upwellings where we have trenches and subduction zones, we have downwellings. Now, if you want to go beyond these cartoons and describe the motions within the mantle, we have to solve certain conservation equations. So we have the two conservation equations of momentum and mass, which describe an instantaneous balance. And then we have the conservation equation of energy, which describes the time evolution of mantle convection. Now, you need to solve these equations. We've had also so much progress solving these equations over the past decades. Nowadays, there are many numerical models available. These models are getting more and more complex. They include nonlinear rheology, thermochemical flow. However, the main problem with them is that they lack first principle physics. And they're mostly based on parameterization of some observations. So it's necessary to test these models on the underlying assumptions. And when we have reliable models that can be tested against observations, we can use them to fill the gap in our knowledge about the past. Now, what is the situation? We are at present day. When we talk about testing of the models, we are at present day. We have information from seismic tomography. We have images of the inner Earth. What we can do, we can solve the equations, go forward in time. Now, the problem is the time scales are really long. We're not going to have any observations about the future system states. What we can do is go back in time. There we have geology and all the observations regarding dynamic topography. Now, the problem is going back in time with negative time steps because of the diffusive processes. These processes are unstable. So just going back in time with negative time steps is not an option. And geodynamicists have used many tricks for the past few years. They've come up with different methods. And the method that I'm going to talk about is an optimization technique using the Adjoint method, which is basically reformulating the problem into an inverse problem instead of a forward problem. How does it work? Let's simplify the whole problem into two dimensions. One dimension is the time we start there. The Earth has started from some temperature at T naught and has convected forward, has evolved in time, and has arrived at the present day. Now, at this point, this is where we have the observations from seismic tomography. We convert it to temperature through some mapping. We can discuss it later, how these mappings work. Then, because we have no knowledge of the initial condition, we start from somewhere that is necessarily different from the actual initial condition. We convect forward, we arrive at present day. Now, what we see, what we can measure at this point is the difference between our model, what the model predicts about the current temperature field of the Earth, and our observation. We can measure this difference mathematically, and we can just express it into some L2 norm, basically the integration of the temperature differences. Now, ideally, I can define this, I can say that if the difference between these two is minimized, I can say that the difference between these two is minimized. So basically, my problem is projected into this problem. What is the ideal initial temperature such that this difference is minimized? Now, for that, if I want to solve this problem, what I need is the misfit derivative of this term with respect to this term, which is my control parameter. So basically, I want the gradient information. Why is that? Now, we can describe the surface of all the possible temperatures that we have. Imagine that you have a surface in the space, and every combination of initial temperature ends up being a certain misfit in the end. Now, ideally, I want to start from here, which is my starting point, and I want to find my way down this surface to the minimum of this misfit, which is basically describing this difference. Now, the guide at each point that I am is this derivative information. Now, this derivative information can be obtained by using the adjoint equations. This is where the name adjoint method comes in. So the adjoint equation gives me the gradient information. I start from iteration 0. I have the direction information. I go another iteration. I move forward along that path. I have the gradient information. And finally, after doing n iterations, depending on different methods, I can end up being at the minimum of this surface. And being at the minimum basically means that I've minimized the misfit and my initial condition is better. Now, let's see in action how it works. Let's go through some synthetic tests. The synthetic test is what we usually call a twin experiment. In a twin experiment, we have a reference simulation. Now, the reference simulation has known initial condition. We start from here, we convect forward, we arrive here. This is the final state. Now, in a twin experiment, this is our known twin. We want to emulate what we have through seismic tomography. What we have is this final state, and we throw away this initial condition knowledge that we have. Now, our goal is just to use this final state here, and using this final state, we want to reconstruct the evolution of the convection, the reference simulation that we have. So basically, we say we don't know anything better. We start from the final state that tomography has given us. We convect forward, we arrive here. And when we are here, we have we can compare our final state with the reference final state. We compute the misfit. We have the gradient information. We go back and correct our initial state. And we do it iteratively after 6 iterations. For example, in this example, visually, our initial and final states are comparable with the reference state. Now, we can also measure the L2 norm, the initial and final condition, and we see that the whole thing is working. Now, I've gone through the motivation. I've talked about the adjoint method, and now what I'm going to do, I'm going to take you through the recent paper that we've published where we discussed, for example, the reconstructions of dynamic topography for the past 50 million years. Now, in total, there are 8 different models. These models go back to 50 million years. They are using compressible formulation of the equations. They are relatively high resolution. Each model is about 600 million grid points. Each model takes enormous amount of CPU time because of the iterative nature of the problem. Now, in this, within the sort of uncertainties that we have, we've tried to tackle the problem by just choosing admissible values for important parameters. One of these parameters is rheology. There is a great uncertainty over rheology and how it changes with depth. We use two published studies of the viscosity profile of the Earth from Photo, Mitrovica, and Steinberger and Calderwood. In addition to that, we invert the viscosity profile really simplistically using three parameters, one for the asthenosphere, one for the upper mantle and lower mantle. This is the green profile that we use. We invert it for geoid and some observations of CMB topography. And because of the uncertainty in the insensitivity of the lower mantle values to these set of observations, we add another viscosity profile in the lower mantle, which covers the uncertainty that we have regarding the lower mantle values. So throughout this talk, I'm going to show simulations with green profile, a red profile, which is the higher value of viscosity in lower mantle, and some reconstruction models with the green one, which is the lower value, because these two basically represent the uncertainty that we have in lower mantle viscosity. Now, for present day, I use two whole tomography models of the mantle, one from Simmons and colleagues, and the other one from French and Romanovich. In the upper mantle, I improved these models by just fading them into the model from Schaefer-Lebedev. I convert these end states to temperature using self-consistent models of phantom mineralogy, basically simulations through Perplex. And I include some anelasticity models from Camarano et al., which describe the nonlinearity in these conversions. Now, for the upper velocity, for the upper boundary of my problem, for the upper surface, I use a plate reconstruction from Miller et al. Because there is not much uncertainty for the time period I'm going to talk about, I'm not changing this, but I'd like to mention that this is one of the pathways in the future of changing these reconstruction models, especially if we go to longer times than 50 million years. Now, in terms of minimization, this is how it looks like our reference at present day. This is using the tomography model by Simmons and colleagues and a Schaefer-Lebedev in the uppermost mantle. I'm using the mu2 viscosity profile. We use this as the initial condition. We convect forward and we see that the structure is significantly different from what we see in the reference final condition. And here I'm showing the misfit, which most of the domain is actually a high misfit. We go through iterations, as you see after 5 iterations, the difference has become significantly lower. The structure already looks like the same as the so-called LVPs in the lower mantle. The misfit has decreased significantly, and we can continue it forward over and over and make it even smaller, and we can even go further than that. Now, the problem is there is a significant uncertainty with the seismic images of the mantle. And in order to avoid any overfitting of the problem, we should either use some regularization. In our formulation, we don't have an actual regularization. So what we do, we use an early stopping method. So basically we stop our iterative approach. We analyze actually the iterative approach only after 5 iterations. Now, this is the higher viscosity in the lower mantle. This is a global model having reconstructions of dynamic topography in time for certain parameters. Now, for the rest of this talk, for the rest of actually this section, I'm going to talk specifically about 3 regions. One is Australia, the other one is Africa, and the other one is North America. I'm going to go through some observations that I'm aware of. I'd like to discuss it at the end of this talk. Is there are any other observations? But basically, I want to take you through the observations and discuss what we see in these models, if we can fit the observations or not. So the first case is Australia. Australia is known for its northeast southwest tilt since the early Miocene. The first observation that we have is basically looking at the early Miocene shorelines. In the north is located further offshore, whereas in the south is located further inland. Now we can zoom in, for example, in the south, Nullarbor plain, basically sedimentary, marine sediments uplifted since the early Miocene. We can look at the northern shore, basically Carpentaria Basin. This is from the study from DiCaprio et al. And basically from 20 million years ago, there is an increase, 20 million years ago, there is an increase in their interpretation of inundation in the northern part of Australia. And you can reason that this could be a sea level effect, but actually when you look at the sea level curves for the past 70 million years, these are so these are different. The trend is actually opposite to what we see from sea level curves. So basically this can be interpreted as subsidence. The northwestern shelf, the same thing. So basically between 10 and 8 million years ago, there is an ongoing further, actually starting from 10 million years ago, there is an increase in the accommodation space. This can be interpreted as about 600 meters of subsidence in 10 million years, which is beyond any sea level effect. Now, what do these models show? This is one specific model that actually shows some of these features. Australia starts from a low standing position. As it moves forward towards a subduction zone, there is an uplift in the south, and simultaneously towards northwest, there is a subsidence signal. And later on at 10 million years, there is another subsidence signal towards north, while there is uplift in the south. Now, the rates of it, if you look at the rates, we had 600 meters in 10 million years. Here we have similar rates of about tens of meters in a million year of subsidence. Now, the next place that we look at is North America. North America is also known for the interior seaway, the Cretaceous interior seaway. This is from the study of Michiriko et al., where they look at the lower Cretaceous isopods, which is consistent with the idea of interior seaway. Basically, the take-home message is that by the end of during the Cretaceous, much of the interior part of North America has been flooded. Now, what is the situation at present day? We look at, for example, Colorado Plateau, where we have marine sediments that are standing about 1 kilometer above sea level. Now, people have used different techniques to reconstruct dynamic topography in time, and this specific study is from Roberts et al., where they use a collection of river profiles in North America, and they try to fit the present day structure and come up with a reconstruction of dynamic topography. And the conclusion from their study is that basically there is a significant episode of uplift starting from 25 million years, continuing to present day, and there is another significant uplift at present at 5 million years. Now, is this the whole story? There is also another story from a northeastern margin of North American continent, where they find, Steckler and Watts find that there is a sudden increase in the accommodation space in the sedimentation about 20 million years, which is also consistent with the idea of the northeastern margin subsiding at around this time. Now, do we see the same thing, the same model? We look at it at 50 million years ago. So basically, this is the dynamic topography signal at 50 million years. On the right-hand side, I forgot to say in the previous slide, this is the dynamic topography rate. This is basically this time stage minus the time stage before, divided by the time difference between them. So this gives us a sense of rate. So 50 million years ago, there is a band of negative signal in the interior of North America. As the continent is moving to west, there is wave of positive signal rate coming towards west. So basically an uplift happening in the interior of the continent as the continent moves west to present day, continuing to present day. At the same time, starting at 20 million years ago, there is subsidence seen in this model on the northeastern margin of the North American continent. Now, moving to Africa, the next place, Africa is known for its basin and swell morphology. Now, I'm aware of the ongoing debate about the age of the present elevation of Africa. There is this discussion about how old it is. Some people say it's pretty recent, some people say it's pretty late. But the most important thing is that Africa has two main features. One is the long wavelength high topography, which is basically visible towards south of Africa, and there is obviously the shorter wavelength towards north of the swells. Now, people, again, this is a study from Paul and colleagues that have used the river profiles over Africa under the assumption that prior to 35 million years, 40 million years, much of the African continent has been low standing, so it's not been at the present elevation. Based on their models, they first see an uplift in the north of the appearance of the swells, which shows up next around the East African system. And another phase of uplift shows up around 20 million years, starting from 20 million years towards the southern part of the continent, which shows up an uplift around South African plateau. Now, another study which is partially in contrast to what we saw is the study from Bobby et al., which they studied the sedimentation around the southern margin of the African continent. And basically from their analysis, it comes out that much of the elevation in Africa is actually old, prior to 100 million years. And much of this period between 1725 is a quiescence period with another phase of uplift at between 25 and 15. Now, this is where it gets interesting, because the same model that we saw for previous regions actually is behaving differently than these observations. So this is Africa 50 million years ago. For much of this time, actually, Africa is low-lying, so low-standing negative signal is observed there. And as we go forward, there is not much uplift signal observed in this model for the high viscosity. This is basically the high viscosity model until pretty late at 10 million years ago, where we see an uplift around the East African rift system, and also we see some shorter wavelength uplifts around the northern part. This is clearly way later than when these events should happen in Africa. Now, the idea here is that, okay, these reconstructions I've been showing, it's been using higher viscosity in the lower mantle, and everything's happening so late. So natural conclusion here would be, okay, can we just decrease the viscosity, fasten things up so we can have things happening at the right time? So we can change the model. We look at the lower viscosity. So everything is the same between these two models. The only thing that is different is the viscosity in the lower mantle is an order of magnitude lower. In this model, what happens is that the African continent starts with high dynamic topography, positive dynamic topography. As we move north, this high standing topography fades away. Basically, there is subsidence in the northwest, and there is subsidence in the south. As we come forward in time, there is another phase of uplift in the south. However, in the north, we see subsidence, and there is no another signal of uplift there. So clearly, things happen way faster than the observations say, and there is two phases of uplift, which is not consistent with the observations that we went through. Now, I went through the reconstruction models. And now this is the part that we have to reflect. Okay, what have we learned? And I actually originally wanted to use the phrase "all models are wrong." What is it that we learn from them? So clearly, for the case of Africa, there is something wrong in these models. Now, because these are models, these can relate topography at the surface to the internal structure of the Earth, we can look at actually what is happening. So this is the model with the higher viscosity in the lower mantle. And we can look at the evolution of the structure beneath Africa. So this is a shear cut, there's a cross section over Africa from west to the east. So the blue point here is this blue point here, and the red point is here. And what we see here, starting from 50 million years ago, is that the structure beneath Africa is reconstructed a bit wider. As we come to present day, this is what we observe that generates the uplift around the East African rift system. And the whole thing happens so much slower than we expect. So basically, the arrival of the afar plume is delayed to present day. Now, we can look at this structure from a 2D point of view. So here I have the time scale and the basically vertical scale. I go from 50 million years to present day. And I have the evolution, the temperature evolution of this model here and this column. Now, in order to adjust things to see why is it that things happen slower than expected, we can change the tomography model. And basically what we see is that even by changing the tomography model, not much changes. These two models reconstruct the structure of the LSVP more or less the same way that they're observed at present day at 50 million years ago. Now, what happens if I choose a lower viscosity value for these models? What happens is that the magnitude of the velocities are increased by about more or less an order of magnitude. So instead of 8 centimeters per year, I have about 10 centimeters per year. The adjoint still does its work. It tries to find the best fitting structure that can represent the structures of the deep mantle. However, such low viscosity, so an order of magnitude lower viscosity, results in significant change in the shape of the LSVP if you go back 50 million years ago. Now, there is clearly something wrong. So these models with higher viscosity, they more or less have the same structure of the LSVPs for the past 50 million years, which is more or less consistent with our expectation. The problem is they are way slower in terms of evolution of dynamic topography over Africa. These models come up with the faster rate. However, there is a significant change in these in this structure beneath Africa. So clearly there is clearly there is something wrong, and there are 3 possible scenarios that we can talk about. The first one is there is an inconsistency in the seismic images and the viscosity that we know from lower mantle. This is especially the case, for example, if you look at the p-diffracted topography model of the Oxford group or the recent transdimensional tomography model of the D-double prime layer by the ANU group. The structure that these recent tomography models show from deep mantle is significantly different from the wavelength. The next one is that basically there is uncertainty, and if we mitigate these uncertainties with some sort of regularization, maybe all these changes would go away. But still, the fact that there is using the observation of present day, we come up with this significant variation in 50 million years is going to be there. We can just mitigate that with some regularization. Now, the other cause that can open up a new path of like research for us in the future is talking about the existence of larger scale chemical heterogeneities in the mantle. Now, the LLVPs have been the focus of such large scale chemical heterogeneities in the mantle. Research in the past has shown that in both thermal and thermochemical models, we can come up with models. So models that are purely thermal and models that are both thermal and chemical in the heterogeneities in the mantle that can come up with the structures that resemble the structure that we see from seismic tomography. Now, the seismic observations that we have had in the past is pretty insensitive to the to things being thermal or thermochemical. So in the absence of any sensitive evidence, people are on both sides of the aisle, so basically thermal versus thermochemical. Now, this is going to be, this is what we're doing right now, working on the on trying to include thermochemical convection in the adjoints in our group. And this is probably one of the paths that we're going to try in the future for trying to see if we can come up with a right dynamic topography reconstruction for Africa. Now, the conclusions I have is basically most of the things that I've said is come to the conclusion that Mantle convection circulations now with the including the reconstruction models can generate synergies across many other disciplines, for example, past sea level studies, paleoclimates, or for example, rotation motion of the Earth. Any assumption, for example, the thermochemical structure of the piles can be tested through these models, and these models can be tested against the observations from geology that are gleaned from geology, for example, evolution of dynamic topography. There are simplifications in the theory, there is uncertainty that we have to account for, and the other important thing is that up until now, we've only relied on seismic tomography at present day. There are other sources of data that we can use to improve these models in time. All of these points about what we want to do in the future, this is what we're working on through the GEDA project. And if you're interested, I know that Rodri is going to present for 10 minutes in the ALSCO conference soon. So if you're interested to know how we are going to account for all these complications, different sets of data, you can go see that talk. The other work that we're doing currently with Mark and Fred Richards and some of the other colleagues is looking at the thermochemical nature of the piles and trying to find the best fitting parameters for that. If you're interested, this is a paper under revision, and I'm happy to discuss that also after this talk. Yep, that was the talk. I kept it short, so I hope it's all right.